Welcome back, everyone. So in this video, we're going to talk about graphs of exponential functions specifically. In the next video, I'll talk about logarithmic functions. So just kind of diving right in, we're going to look at key characteristics of exponential functions. So the equation form that we're going to be looking at is going to be f of x equals a times b raised to the x, where your b value is going to represent a positive number, and then your a and b values are going to be constants, where a is not equal to 1 and b is not equal, where a is not equal to 0 and b is not equal to 1. There we go. So looking at this equation, your a value specifically is going to represent your initial amount. Now, when I say initial amount, this is also another way of saying your y-intercept, which that's going to be a very important feature when we get to applications. And then your b value, in this case, since we already covered sequences, this also represents your common ratio, which we know from geometric sequences. Now, of course, in terms of exponential functions, we are going to know this as a growth rate. So tomato, tomato, just know that we could go back and forth between both of those. So we're going to start off with just looking at the end behavior for exponential growth. Now, starting off, just being fully transparent, I'm going to do the end behavior just for this type of exponential growth. So just looking at this particular graph. But there may be other instances where that would change your end behavior based on transformations or depending on the situation that we're looking at. So if I look at my end behavior of this particular graph, I'm going to be going left indefinitely, and it's going to be approaching your horizontal asymptote, which in this case is going to be y equals 0. And then as I go to the right indefinitely, I'm going to be going up towards infinity. So looking at my end behavior, so this is going to be the limit as x approaches negative infinity of f of x, and then it's going to approach whatever your horizontal asymptote is in this case, which in this case is going to be 0. And then my right-sided behavior, so limit as x is approaching positive infinity of f of x, it's going up indefinitely, which means it's going to be positive infinity. Now, looking at the next one, now we're going to look at what we call an exponential decay. Now, to determine the difference between an exponential growth and decay, we're looking particularly at the b value. So if your b value is greater than 1, that's going to be an exponential growth. Whereas if your b value is between 0 and 1, that's going to be an exponential decay. So your exponential growth right here is going to be going either away from your horizontal asymptote in either direction, whereas a decay would be getting closer to your asymptote. So we'll look at different variations of those graphs, but this idea is going to be pretty important. So now looking at the end behavior of this exponential decay, so now as I go left indefinitely, my graph is increasing, and then as I go right indefinitely, then my function here levels off. So my end behavior, my limit as x approaches negative infinity of f of x, is going to approach positive infinity, but my limit as x approaches positive infinity of f of x is going to equal my horizontal asymptote, which in this case is going to be 0. So now looking at your increasing, decreasing, and your concavity for these exponential functions, just know that exponential functions are always increasing or decreasing. They're not going to switch directions. And then same idea with concavity. They're always going to be concave up or always concave down. They never switch. So looking down here, we're going to kind of build on the end behavior. So if I have this function down here, we have an exponential equation. So we have our horizontal asymptote, which is going to be at y equals 0. So for my limit statement, so we're going to have the limit as x is approaching negative infinity of f of x, and that's going to equal 0. And then my limit as x is approaching positive infinity, so on the right side of f of x, that's going to equal positive infinity. So notice how these graphs over here, they don't give you a function title or a function name. So just by default, you're just going to use f of x. So now looking at this graph here, So once again, if I go to the left, we're going down indefinitely, and if I go to the right, we're leveling off. So what this tells me, it's my limit as x approaches negative infinity of f of x, that's going to equal negative infinity. And then my limit as x is approaching positive infinity, we're leveling off in this case, which means it's going to be my horizontal asymptote, which in this case we're going to say is 0. Now looking at part C over here, now we have g of x equals 5 parentheses 2/3 x. So in this case, you are going to be given an equation, and you have to recognize based on the b value if this would be a growth or a decay. Now, because we have a b value of 2/3, that is less than 1, which tells me it's going to be a decay. So my graph, because it's positive and it's a decay, it's going to follow something like this. So this would be kind of a general idea of what your graph looks like. So for my limit notation, so my limit as x approaches negative infinity of g of x, so in this case we do have a function name, so you've got to make sure that you're using the correct letter in your limit notation. So my limit as x approaches negative infinity of g of x is going to equal positive infinity, and then my limit as x is approaching positive infinity of g of x, in this case, is going to equal your horizontal asymptote, which in this case is 0. Now, a common question I get is, how do I know what the horizontal asymptote is? Well, based on transformations, that is going to be the value that is either being added or subtracted here at the very end. So this would be your horizontal asymptote. So like if I was adding 5, then I'd have a horizontal asymptote of 5. If I was subtracting 3, then I'd have a horizontal asymptote at -3. So it's whatever that vertical shift is. All right, now looking down here, now we're going to look at increasing, decreasing, and concavity. So looking at this first graph, my graph is going to be decreasing, so my y values are going to be getting smaller as I go along. And then my graph is also going to be concave up, if you look at the shape. So this graph is decreasing, and that's terrible, and concave up. Then if I look at the next part over here, I'm going to do these a little bit quicker. So my graph is going to be decreasing and concave down, since we're facing downwards. And then over here, if I look at part C, g of x equals 3 times 4 raised to the x. So my b value here is bigger than 1, so we're looking at an exponential growth. So your graph is going to look something like this. So that means we're increasing and concave up. So before we look on to the next part, we're going to review some really important exponent rules that are going to be necessary for the next part. So looking at product property, if the base is written more than once, and I have these exponents here, what we're going to do is we're going to add these exponents together. So I'm going to have x raised to the m plus n. So for example, I have these examples here. So I have x raised to the 5th times x raised to the 3rd power. I'm going to add these exponents together, which is going to give me x raised to the 8th power. And then down below, we have b raised to the x, b raised to the 2nd power, and then b. Now right here, I don't have an exponent written, so if there's nothing written, you assume there's a 1. And then we're going to add them all together. So b raised to the x plus 2 plus 1, which is going to be b raised to the x plus 3. So this would be your simplified value. And then looking at power property. So with power property, now if I have the base written just once and I'm raising a power to another power, we're going to multiply these values. So this is going to be x raised to the m times n. So as an example, h squared raised to the 5th is going to be h raised to the 2 times 5, which is going to be h raised to the 10th. And then down below, we have 2 raised to the x all raised to the 3rd power, which is going to be 2 raised to the 3x. So I'm going to multiply those values together. Now notice when I look at both of these properties, the base over here in product property, the base is written more than once. But over in power property, the base is only written one time. So I look to see how many times the base is written. That's kind of my indicator as to which property I'm doing. Because when you look at it on paper, when you're doing problems, these properties are going to look very similar. So now with exponent property, or the negative exponent property. So with this, what this tells me is if I have some base value raised to a negative exponent, what's going to happen is you're going to find the reciprocal of it. So I'm going to rewrite this as x raised to the negative n all over 1. And then when I have a negative exponent, I'm going to move this value in the denominator. I'm going to move it to the, nope, it's in the numerator. I'm going to move it to the denominator. And then when I move it, it's going to become positive. So now that I have nothing left in the numerator, we're going to have 1 over x raised to the positive n power. So when I do switch its sides from top to bottom or even bottom to top, then the value of that exponent is going to become positive, or it's going to flip signs rather, I guess would be the more precise way of saying that. So if I look at the next one, so if I have t raised to a negative w, that's the same as writing 1 over t to the positive w power. And then 1 over 3 to a negative e power, I'm going to bring it up to the top, so that'd be 3 raised to the positive v over 1. And then because I don't have any value other than 1 in the denominator, I can just rewrite it as just 3 raised to the positive v. So now what we're going to do is we're going to look at these transformations. So we're going to use transformations and exponent properties. We're going to combine these two concepts when we get to this bottom part down here. So starting off, I have these 4 functions, and we want to determine the horizontal transformations of each of the following. So right here I have f of x equals 4 raised to the x plus 2. What you need to determine is what the parent function is of this equation. So if I look here, the original of this would just be 4 raised to the x. So I want to compare it with what I have here. So that plus 2 is what's going to be different. So that means I'm going to go left 2. Now if I look at part B, my original function here is just going to be y equals, I should have did y equals over here. So it's going to be y equals 2 raised to the x. So then my transformation is going to be this 3 right here. Now when I say my original function, we're looking at whatever the base is raised to that variable. So just like over here on part A, whatever the base is raised to that variable, that's going to be your parent. So when I look over here, we have g of x equals 2 raised to the 3x. This is going to be a horizontal dilation. So this would be horizontal dilation of 1/3. So remember, with those horizontal dilations, you got to flip it. Now if I look over at part C, so my original function here, we're going to have y equals 9 raised to the x. So this is the same as writing 9 raised to the 1/2 x, which means we're going to have a horizontal dilation of 2. And then next over here, so part D, we're going to have parent function of 5 raised to the x. So my transformations here, I'm going to rewrite, factor out that negative 2. So we're going to have x minus 1/2. So my transformations here, we're going to have a reflection over the y-axis. And then we're going to have a horizontal dilation of 1/2. And then we're going to go right 1/2. So the reflection over the y-axis, horizontal dilation of 1/2, and then we're going to go right 1/2. So those are where all those transformations are coming from. So next, now what we're going to do is I want to rewrite any horizontal translations. I'm going to rewrite them as vertical dilations. So with exponential functions, your transformations could actually be written a couple different ways. So starting off on number 4 here, so once again, we're looking for what's the parent function. So in this case, we're going to have just y equals 2 raised to the x. So my horizontal translation in this case would be a left 3. So horizontal translation over here in this box, I'm just going to say left 3. Now what I want to do next is I want to see, okay, left 3 would be the same as what type of vertical dilation. So over here, I'm actually going to rewrite my equation. So I have y equals 2 raised to the x plus 3. And then what I want to do is I'm going to use my exponent properties. Particularly, I'm going to use product property for this first part. So I have it written as a sum, but what I want to do is I actually want to split it up. So I want to see 2 distinct terms. So what's going to happen is I'm going to split and rewrite as 2 raised to the x times 2 raised to the third. And then I can rewrite 2 raised to the third. I can simplify that value. This would be y equals 2 raised to the x, and then that's going to be times 8. And then I'm going to rewrite with my 8 value in the front, which means I'm going to have y equals 8 times 2 raised to the x. So my vertical dilation is going to be my a value. So in this case, going left 3 is the same as a vertical dilation of 8. So I would say pause here and actually try 5 and 6 on your own. But I'm going to keep going. So parent function, we're going to start off with just y equals 3 raised to the x. And then I'm going to rewrite my function over here. So we're going to have y equals 3 raised to the x minus 2. And I'm going to split. So y is going to be equal 3 raised to the x times 3 raised to the negative 2. And I'm going to rewrite 3 to the negative 2. So we have y equals 3 raised to the x times, that's going to be 1 over 3 squared. So this is the same as y equals 3 raised to the x times 1 over 9. And I'm going to rewrite it so that I put my 1/9 in the front. So we have 1/9 times 3 raised to the x. So in this case, I'm not going to write it out. I'm just going to verbally say it. A shift right 2 units in this case is the same as a vertical dilation of 1/9. Okay, and then over here. So now a parent function, we're going to look at y equals just 3 raised to the x. And now I want to start rewriting. So we're going to have 4 parentheses 3 raised to the x times 3 raised to the second. And I'm going to rewrite. So 4 times 3 raised to the x times 3 squared, which is 9. And I'm going to rewrite 9 times 4. So that would be 36 times 3 raised to the x. So in this case, a shift left 2 for this equation is the same as a vertical dilation of 36. So now we're going to kind of put all that information together in these problems here. So we have 6 problems. I may or may not do all of them. I don't know yet. We'll see. So we're going to determine all the following attributes. So we have f of x equals 2 raised to the x plus 3. We want to list out the transformations, the corresponding asymptote, if it's increasing, decreasing, concave up or down. And then the graph this is going to be a written description based on increasing in concavity, or increasing, decreasing in concavity. And then we're going to look at the domain and range and the end behavior. Okay, so starting off, I'm going to do the transformations both from the original function, but I'm also going to do transformations when it's rewritten. I can never remember if rewritten has 2 T's or 1 T. It's fine. This is why I teach math and not English. Okay, anyways. So looking at the original function, I can see that we have a shift left of 3. So I'm going to say left 3. And now I want to rewrite it so I can see what it's going to translate to in terms of a vertical dilation. So when I separate, so we're going to have 2 raised to the x times 2 raised to the third power. Well, 2 raised to the third power is 8. So I'm going to move that 8 to the front. So this is the same as a vertical dilation of 8. So now looking at my asymptotes, so I don't have a d value or anything, so my equation, just kind of a rough sketch, is going to look something like this. Since we have a growth, since my b value is bigger than 1, so my asymptote is going to be a horizontal asymptote at just y equals 0, since we don't have a vertical shift. So asymptote would just be y equals 0. My graph is going to be going upwards as my x value increases, which tells me it's increasing. And then looking at the shape of my graph here, it's concave up. And then my graph here, so what I want to put here is kind of the description of the graph in regards to its average rate of change. So meaning the graph is increasing at an increasing rate. Okay, and then my domain of my exponential function, it's going to go left indefinitely, and it's going to go right indefinitely. So my domain is going to be all real numbers. And then my range, well, because of that horizontal asymptote, I want everything above that horizontal asymptote, which means I want to go from 0 to positive infinity. And then for my end behavior, so as you can kind of see from a visual of my graph, as I go to the left, we're getting closer to the horizontal asymptote, and then as I go to the right, we're getting closer and closer to infinity. So for my end behavior, I'm going to say my limit as x is approaching negative infinity. Is it f of x? Yes, it is. Of f of x, and that's going to equal the horizontal asymptote, which in this case is 0. And then my limit as x is approaching positive infinity of f of x, which is going to equal positive infinity. All right, so now, let's just do 8 and 9, I guess. So now with this one, so same idea. I want to look at my original equation, and then I want to look at the transformations. But when I look at the transformations, I want to look at both the original, and I also want to look at the rewritten. So looking here, so I'm going to just start with the original. So we have a reflection over the x-axis, left 1, and then up 4. So a reflection over the x-axis, which I'm going to shorthand as r sub x, and then left 1, and then I also have up 4. So now I want to rewrite it and see what those translations are going to translate to in terms of vertical dilations. But more specifically, I want to look to see what the horizontal translation will translate to in terms of a dilation. So when I rewrite, so I'm going to have negative parentheses 3 raised to the x, and then 3 raised to the first, then plus 4. So when I rewrite, 3 to the first power is just 3, so I'm going to move this 3 over here to the front. So this is negative 3 parentheses 3 raised to the x plus 4. So when I rewrite, we still have a reflection over the x-axis, and now I have a vertical dilation of 3. So v dilation of 3. And then I still have that shift up of 4. So I'll say up 4. So notice how, nope, you can see all my pictures go away. So notice how the translation now turned into a vertical dilation. So that's why I like to look at both of these. So with my asymptote, so we had a shift up, so this plus 4 right here, that is my asymptote. So this is going to be an asymptote of y equals 4. And then if I want to do a visual of my graph, so I look to see, okay, my growth rate here, my b value, is bigger than 1, but then I also have a reflection over the x-axis. So my graph is going to look generally something like this. And then the asymptote that is going to get closer and closer to, this is going to be y equals 4. So now looking at my graphs, so looking at my graph, I can see it's going to be decreasing and that it's also going to be concave down. And then what that tells me is my graph is going to be decreasing at a decreasing rate. So what I want you to kind of put together is I'm using the increasing, decreasing, and concavity to write this statement. So since I'm decreasing in concave down, the decreasing is going to correspond to the first decreasing. That's going to refer to the direction. And then the concavity is going to tell you if it's an increasing or decreasing rate. So in this case, if I look at the first one, I'm increasing at an increasing rate. Over here, I'm decreasing at a decreasing rate. Or if I was increasing and concave down, I would say I'm increasing at a decreasing rate, or vice versa. If I was decreasing but concave up, then I would say I am decreasing at an increasing rate. So this is kind of your sentence stem to help you start with the next statement. So with the domain, we're still going left and right indefinitely. So domain for exponentials is going to be all real numbers. And then my range, you're going to have to pay attention to your horizontal asymptote and the direction your graph is going. So I want everything below y equals 4. So what that tells me is I want to go from negative infinity to positive 4. Okay, and then my end behavior, so as I go to the left, I'm leveling off, so I would get closer and closer to my horizontal asymptote. And then as I go to the right, I'm going down towards negative infinity. So for my end behavior, what's going to happen here, so I'm going to have the limit as x approaches negative infinity, and then make sure you use the correct letter, which in this case is g of x. And that's going to equal the horizontal asymptote, which in this case, it's going to be equal to 4. And then my limit as x is approaching positive infinity of g of x, it's going down indefinitely, which tells me it's going to equal negative infinity. All right, so now in this case, let me take a quick little sneak peek at these other ones to see if we can get a little bit of variation in here. I don't want to do the same thing. Okay, yeah, number 9 is going to be a good one to do. Okay, so I would actually say pause here, try number 9 on your own. You can compare it to what I have on 7 and 8, but I would say try it on your own first. So, transformations, once again, I'm going to do the original. And then I'm also going to do the rewritten. All right, so looking at my transformations, so I have a reflection over the x-axis, I have a vertical dilation of 8, a reflection over the y-axis, and then when I take that out, take out a negative, then I'm going to have -3, which means I'm going to go right 3, and then up 2. So I'm going to write out all that garbage. All right, so I have reflection over the x-axis, vertical dilation of 8. Then I also have a reflection over the y-axis. Then we're going to go right 3 when you factor out that negative. And then I'm also going to go up 2. So now let's rewrite. So when I rewrite, so -8, then parentheses, 4 raised to the negative x, and then 4 raised to the third. Now notice how when I rewrite, I'm not going to factor out anything. I'm going to leave it exactly how it is, and I'm just going to separate. And then +2. So when I rewrite, I'm going to have -8, and then I'm going to use my negative exponent properties here. 4 raised to a negative x is going to turn into 1/4 raised to the x. And then 4 cubed, that's going to turn into, I believe it's 64. And then, of course, we still have that +2 at the very end. So now I want to multiply my 64 and -8. And then those are going to become -512, parentheses, 1/4 raised to the x plus 2. So when I look at this shape, I'm going to have a decay, since I have a 1/4 here. So it's going to look generally like something like this. But then I have a reflection over the x-axis, which means that now it's going to go something like this. So my graph is actually going to go and follow this shape. And then the top over here where it kind of levels off, that's going to be my horizontal asymptote. So that would be a y value of 2. So now let's fill in. Oh, I didn't do my transformations. So based on the rewritten, we're going to have a reflection over the x-axis, a vertical dilation of 512, and then we're going to go up 2. So when I rewrite, a lot of these transformations over here in the original actually get condensed into just the vertical dilation of 512. So my asymptote, which as we know is just y equals 2. Then when I look at my graph, it is increasing, but we are also concave down, which tells me that I'm going to be increasing at a decreasing rate. And then, of course, domain would be all real numbers for exponentials. Whereas the range, we want everything below the horizontal asymptote, so I want everything below 2, which means I want from negative infinity to positive 2. And then for my end behavior, so check the letter, we are using h of x. So my limit as x approaches negative infinity of h of x, that is going to equal negative infinity, since we're going down indefinitely on that left side. And then my limit as x approaches positive infinity of h of x is going to equal the horizontal asymptote, which in this case is going to be 2. So I would definitely encourage you to try these last 3 on your own. Make good choices.